Hello people, welcome back to my channel. Today in this video we'll be seeing cluster validation approach and also how we can visualize the results in by using the silhouette coefficient. And there are certain libraries which are available from the scikit-learn library from where you can do this activity. So let's begin. So first of all, today in this session we'll be discussing, or I'll be introducing about certain few libraries which we have not come across from any of the past videos. Okay, and I'll be also discussing about a new technique by which you can generate a data set randomly. So that's also possible, not the other way by how like we generate by using the data frames. It's not in that way, but by a different approach we can do that. Okay, so we add some numpy, we add the pandas, then we require the seaborn, then the matplotlib, pyplot as plt. Then we have a scipy spatial distance matrix. Actually, for this purpose, we don't require, but we'll see down the line whether it's required or not. Then sklearn datasets sample generators make blobs. So this is the one which I was talking about. So we are going to make a cluster heat map. So heat map is actually used for visualization purpose. So it will give you the cluster strength, which clusters are very closely related, which are very loosely related. So for that we are making use of a binary large object. So blob stands for binary large object. And so in sklearn there is a library or a method called as make blobs, from which you can do this activity. So I'll just give you a summary of what this thing is. So sklearn datasets make blobs. So what it does is it generates isotropic Gaussian blobs for clustering, that is binary large objects which are images. So you will get pixelated images. So before this also we have come across for correlation analysis and heat maps. So this is a different technique by which we can generate. Okay, so the parameters which it takes are the n samples, the features, uh, and then the centers, cluster standard deviation for the clusters, center box, shuffle, then random state, return centers, and many. But we'll be not using all of this, but a few of this which will be requiring for our purpose. So I'll just put the link in the description. So when you get time, you can visit this website and look for the other parameters. Then we'll require sklearn cluster import k-means. Then from sklearn matrix itself, we have the silhouette score, which will calculate the silhouette coefficient actually. Then from yellow brick cluster, we are importing something called as silhouette visualizer. So first, this is what the sklearn matrix silhouette score is. So it will calculate the silhouette coefficient for all the samples that are available. So uh, we have already did an activity for calculating the silhouette score. So this is a package or a built-in package which you can use to do your activity or visualization purpose. So it's for that. So actually we have gone deep into silhouette, like how we can calculate each of the points A, B, how we calculate the minimum by Euclidean distance and all. So this is just a simple method or a function call from which you can do all the computations. So it will calculate A, B, everything. Okay. So it's for that. And then what we discussed is about silhouette visualizer. So this is from scikit YB, that is yellow bricks. So this silhouette visualizer actually it will give you a visualization of the cluster labels with the silhouette coefficient. So it will give you a comparison in a band like way, which cluster label has which values for silhouette coefficient, which is good, which is bad. So obviously if the silhouette score is negative, that means it will be very bad, so that's not desirable. But there will be some values which will be above average, that will be very good clusterings. So by that we can actually make out like how good that cluster actually is. So for that we'll be having this silhouette visualizer, and then from matplotlib we'll have the RC params that we know. Then from sklearn metrics pairwise we have something called as Manhattan distances. So this is another thing, that is sklearn metrics pairwise Manhattan distances. So here just to keep in mind, like we'll not be using Euclidean distance, just uh, like easier calculation. So for easier calculation we'll be taking the absolute values. So Manhattan distance or city block distance calculates in that way. So for simplicity we'll be using the Manhattan distances, and all the lower values will be better in this case. Okay, so these are the libraries and the methods that we'll be using in this session. And there is something called as import operator. So what this operator is, so it is a standard operator which can be used as functions. So this is one important property or method which is there in Python, by which you can make use of an operator and convert it into a method. Okay, so we'll get into this portion later when we actually see where it is used and why it is used. Okay, so then we have something called as paired distances. So that is basically used for calculating the distance matrix. And we use the SNS set. We set the context and all the textures and figure sizes, etc. So we set the figure size here as 7 cross 5. So first is what we do is we'll generate some k-means data. We don't have as such a data set here. Okay, so it's like the previous case also, we'll be generating on the fly, we'll be declaring some of the parameters, and from that we'll be basically generating our data for k-means, and following we'll be building upon all the visualizations based upon that. Okay, so for the cluster heat map, what we need is some heat map samples. So here we'll just take around 100 samples, just a small set of 100 samples. Then we have something called as heat map cluster standard deviation. So that value we can take it as 0.1. Then we have heat map centers. So uh, basically in the first scenario is like we'll have 100 samples, that is 100 points, and we decide to have three different clusters. So for three clusters we are having three heat map centers, that is 0 0 1 1 2 0. So first of all what we have is we create and cast into a data frame. So we create a data frame by using the make blobs. So we are actually doing the packing operation x comma y. So here if you look at this definition of this method, it has n samples. So here what we take is heat map n samples. We have 100 in numbers. Then the features what we have is we have two features, that is x and y. Then centers, that is heat map centers, that is this three. Okay, then the cluster standard deviation that goes is 0.1, and random state, that is 5. So you can actually read about the random state that it determines random number generation for the dataset creation. So we usually pass an integer. So you can tweak around these parameters and you can see considerable difference when you actually do the clustering. So it's for that purpose. Then we take all of this. So from this we have the X. So from X we actually uh, create a data frame, and it will have two columns X and Y. Okay. So this is the print statement of how it actually looks. So we'll just run the cell uh, later. So I'll just initialize this. Okay. So till here, if it's clear, then we shall run the k-means and sort the points according to the cluster labels. So we invoke the k-means method and we store it into an object called as k-means. So the number of clusters that we require here to have is the length of the heat map centers. So if you look at the heat map centers, those are 3 in number. So this is a list. Length of this list is 3. So we get those as n centers, that is clusters, and the number of iterations that we'll be having is, so 1000 iterations. So after 1000 iterations only we'll get a desired number of 3 clusters which look actually like a cluster. Later we'll check whether that clustering is good or not by silhouette coefficient. Okay. So then we do a model dot fit, like k-means dot fit x the data points, and so this is and y is your test set actually here. So now here what we do is, so in k-means it has a coefficient, like in linear regression we have model dot coefficient. We get those parameters when we do model dot fit. Similarly in k-means you have something called as k-means labels. So that we actually store into a data frame like x of cluster. Okay, so it will get the labels of that, and we basically have to sort those values. Why? Because eventually we are putting, or we want to produce a heat map, so it has to be sorted, else heat map won't look properly or it would be distorted. So for that we'll be actually sorting these values, and then what we do is we create a distance matrix. So that is also a data frame that is a distance matrix. So we'll be making use of the Manhattan distances, that is this one, pairwise Manhattan distances, and in this we'll pass uh, the data set x and y as columns, and then we just plot the results. Okay, as in a scatter plot. On the x-axis it is x, y-axis y, data as x, that is the training set, and the hue that we give it as cluster. So it will be color coded by default what it already has, and plt.show. And for heat map we actually pass this distance matrix, so that will be a symmetric distance matrix, and will pass on to heat map. That is simple. So this is how it looks like. So we have already seen this implementation before also when we did a customer segment analysis. So it looks something like this because the color codes that it gets, that is by default, and this is how the heat map looks. So corresponding to 3 clusters, you can see the darker portion. Okay, so that is along the centers. So this is what the cluster heat map is. Now we'll find the number of clusters in a dataset. Now we have already done this activity in the silhouette coefficient video, the implementation. There we actually did create a data frame, and from data frame we actually did many operations. We calculated A, B, distance and all. So here we'll decide, or we'll see how we can make use of the silhouette visualizer, and from that what inferences we can make out that. Okay, so we'll do a small data visualization and analysis purpose. Okay, so here also the samples that we'll be having is 100 samples, centers 5 means uh, we will have 5 cluster centers, or we desire to have 5 different clusters. The k min, uh, so we'll have 2, so that is the range that we are giving, and k max is 10. So in between 2 to 10 will decide the optimal number of clusters. So we know that we want 5 clusters, but this is just for a routine purpose, that will be plotting the optimal number of k. For k means we have already decided that by using the elbow method. This is a revision, or you can consider a different way by which you can do this activity also. So here also we do the same thing. So we have n samples and features, centers, and random state. So this is same as the before, so from make blobs, and we are converting that into a data frame. And here what we do is we do a scatter plot, that is simple, and plt.show. Now here comes the main part, because here what we have is, usually when we plot any uh, diagram or for elbow method, on the x-axis we'll have the number of clusters, that is the k value, and on the y-axis you have the SSE, that is the sum of squared errors. Usually that is seen, but also we can calibrate this axis and you can make the changes accordingly. So you can also put the silhouette on the y-axis, and on the x-axis you can put the number of clusters. That is also possible. So for that we'll be maintaining this into a dictionary. So we have SSE and SIL as two dictionaries. So this is a for loop. So for each of the clusters we'll be appending that. So for k in the range of k min to k max, so it will run from 2 to 9. It will not go to 10. Okay. So we are calling the k means, that is, or we are generating here the k means object. So from k means we are actually calling this number of clusters, that is k. So the k number of clusters that we want, and the maximum number of iterations, and we'll do a fit. So this is also possible, fit of x, you can dynamically call this. And then here we are calling the k-means labels, and we are passing this on to, or storing it into a data frame x of clusters. Now here what we are actually doing is, uh, so this one single line from the scikit library will calculate the silhouette score. So it is that simple. We need not do all the computations, because that was a uh, way like how we actually do it. Okay, so it's better to know like how and why we calculate each of the values from within cluster, then outside clusters, a values, b values, how it is calculated, taking the average, taking the maximum, then comparing all those things we did in silhouette implementation video. Just this one simple function will do all of these things. So it will take your training set x and the k-means labels, and it will compute the silhouette score and it will store in sil of k. So for each values, k values, it will compute the silhouette score and will plot it. So it is as simple as that. And SSE, so SSE is sum of squared errors. So for that we'll have k means dot inertia. So inertia is nothing but it will calculate the centroids. So it is sum of distances of samples to the cluster center. So uh, that will basically calculate the distance to the cluster centers. So SSE and silhouette. So these are the two things that we require here, and we'll basically plot this thing. So here actually now we want to have three plots. One plot will be for the scatter plot, that is the number of clusters, that is 5 clusters for 100 points. Then what we have is will generate an elbow structure. On the x-axis we have the number of clusters, that is k, and on the y-axis we have the SSC. So here what we are doing is just look here. So that is SSC dot keys. So SSC here is a dictionary. So in dictionary we can get two parameters, dict dot values and dict dot keys. So all the keys that I have from SSC dictionary, I'm converting into a list. So I will have a range of different values. Okay, and this values that also, so this is a SSC dot keys of this dictionary, and this is the values of that. So both I am casting it into a list and then I am using it for plotting. Okay, so one value will actually be the number of clusters, and the other one will be the SSC values. So it is as simple as that. So keys will serve as the number of clusters and values will serve as the SSC values. So that is nothing but this line does actually, and this is nothing but another function from PLT, that is axis vertical line. So what it basically does is it will give you a line where it has a significant bend. So when you said 5 number of clusters that you want to have here, so it will give you a vertical line, AXV line, that is the axis vertical line here, and the line style is hyphenated, so you'll get a hyphenated vertical line where the optimal number of clusters actually is. So this is what this particular line does. Okay, so now that is clear, then we'll plot another figure. So that is with the silhouette coefficient and with the number of clusters. So this is one plot which gives you the number of clusters versus SSC. So that should be an elbow, and this will be not an elbow but will be a recalibrated graph. It will be an inverted structure. So remember, in elbow method we determined the minimum and maximum distance and we joined a line segment. Okay, so that similar kind of graph we will be simulating in this. Okay, so here instead of this line, what difference we can make out is like silhouette keys will serve as the cluster numbers, number of clusters k, and the silhouette values will actually be the values of silhouette coefficients. And here what we have is, so this thing actually you can remember the spike or the maximum crescent which you want to have in your plot. So that will be silhouette items. So from dictionary also you can get sil dot items. So that is also one method which is present in dictionaries, and there is a key. So this is what my operator does is, so if I go here, so operator as standard, operators as functions. So here if you go down, you can read this operator item getter item. So it returns a callable object that fetches an item from its operand using the operand's get item method. So it is as simple as that. So usually it's a standalone code. So it will get the item that has the maximum value and it will exactly place your axis vertical line onto that place where it has the maximum number of clusters or where the peak is maximum. So you can think in that way. So that is about this particular plot. And finally we have used the yellow bricks silhouette visualizer. So in that you actually pass the instance of the model k-means and the colors yellow brick, and then you call visualizer.fit and visualizer.show. Okay, so if this is clear, then we'll just run this cell. Okay, it's ready. So this is how my 5 number of different clusters for 100 data points it looks like. Okay, x and y. This is what I was talking about, the vertical line, and this is the elbow. So now here you can see many significant bends here. So one is at 3, other one is at 4, the other one is at 5. So which is the optimal number? So 5 we gave as optimal number, but just to plot this thing, this line, so that is given by this one. So this serves that purpose of that particular line. Okay, and plotting that line is given by this. So where to place this line, that is defined by this statement, and actually to color code this, okay, that is given by this. So it serves two different purpose. Okay, and this is the recalibrated ones. Now here it was the SC. Now in this plot you can see the silhouette score on the y-axis, and these are the number of clusters. So at 5 you have the maximum peak. So this AX vertical line that remains a constant, but when you change the graphs, the line should not change. So that is the major point in that. So you get this plot in this way, and this is the resultant of what you make use of the yellow bricks silhouette visualizer. So in this, what you can see is actually when you run every time, it will give you different results. So or when you tweak the parameters, you will get different results. So the red dashed line, which you can see, that is the average silhouette coefficient for that cluster. So here we have 0 to 9 cluster labels. Okay, we have 5 clusters, but the cluster labels are 9 in numbers. Okay, so this is how it looks like. So it has given different color codes, and you can see 1 2 3 4 5 6 and 7 clusters uh, that has silhouette scores very good. So those are above average, and there is one, this particular cluster, that is very bad, and it also has a negative value. So negative silhouette coefficients are not entertained, or we don't take that. And also on the y-axis it's not above average, it is actually below average, you can say in that way. Okay, so this is how we can make use of the silhouette values and the cluster labels, and you can make use of the yellow bricks uh, silhouette visualizer, and you can actually plot this thing. uh, there are other tools also by which you can generate. Actually you can make use of in R there is a package, or there is a method itself from where you can do this. Then there is a tool actually which is called as Orange Biolab, Orange. So in that tool also you can reproduce these kinds of diagrams. So this is the way by which you can actually visualize the silhouette scores, and you can make some insights. So well, that was all regarding this cluster heat maps, and introduction to some of the scikit-learn libraries for standard uh, visualizer from yellow bricks, and some of the new things. I hope you got an idea into these methods. So well, that was all regarding in this video. If you found this video helpful, informative, educated, so please don't forget to subscribe to my channel, and thank you very much for watching this video.